Okay, welcome to this third video about solving equations with exponents that are variables. Okay, and you should have watched two previous videos as well as had a good basis of instruction in class around these ideas. The first video talked about using the feel-it method, which you should have developed some sense about around the power tables and be more familiar with those numbers so that they jump out at you like we talked about. And then for ones where you needed to be a little more formal, you could use a change of base in the one-to-one principle where we could rewrite given numbers in a problem with a common base. And now we're going to move on to the log method, which again you should have already seen in class. This is not a primary instruction video, it's just to kind of see more examples, do a little bit more listening to me think out loud, and try and see how these problems go. So let's take a look at these examples here, where it says solving equations with variables in the exponent, the log approach. Directions, solve for x, round to the nearest 10,000th, which is 4 places. Now, if you notice, that wasn't necessary in previous examples because we got either very nice answers in the feel-it method or at least decimal answers in the one-to-one method where they were able to be rationalized. Okay, we might get some really funky numbers here. And if you look at problem 1, you'll have a sense of why that is. You look there and you see it says 7 to the x equals 10. Well, that's a bit of a conundrum because 7 to the first is 7 and 7 squared is 49. So I would guess the answer to get 10 is going to have to be an exponent between 1 and 2. But if you notice, I can't rewrite 7 and 10 with a common base. So that gets me kind of stuck here. Well, I hope what jumps out at you here is just the basic log principle of taking that exponential expression and writing it as a log. So we have a base here of 7, an exponent of x, and what I refer to in class as the to get, because it's what we get when we use that base and that exponent. So hopefully you'll see the way to write this is to say log base 7 of 10, or to get 10, is equal to x. Well, just by doing that, I've now gotten x alone, which is kind of what we do when we solve for x. I didn't do anything clever except rewrite the form. So from here now, we're going to look at the change of base formula, which you probably should have seen, which just says that I'm going to be able to go to my calculator and use base 10 by doing x is equal to log of 10 over log of 7. So now, just going to my calculator and punching that in, it's going to give me hopefully something between 1 and 2 and closer to 1. And to go to 4 decimal places, I'm going to get 1.1833. So x is about 1.1833. So also, if I go to store that on my calculator, 1.1833, store x, and then I do 7 to the x, I should get 10, but I don't. I get something very close to 10, and why was that? It's because I rounded that answer. That's why I'm getting something very close to 10. Okay? So to go back, just a couple lines on my calculator, if you see where I got this, and although I wrote the answer rounded to 4 decimal places, if I would have stored that as x and then done 7 to the x, because I didn't do any rounding, it would give me the exact value of 10. So this answer is legitimate. Okay? And I'll move on to the next example, which we see here is 6 to the x is equal to 1/25. Well, if you notice there, I don't know 6 to the what is going to give me 1/25, and I can't seem to rewrite 6 and 25 with the same base. They're not in the same power table. So it's going to require log. So I just take this expression and rewrite it log with a base of 6 to get 1/25 equals x. It's a pretty quick way to get x by itself. And then from there, you're going to get log 1/25 over log 6 equals x. And you'll see that'll give me a pretty funky decimal, which I would expect for this problem. And I would just do log 1/25, making sure I use my parentheses correctly, divided by log of 6. And this is giving me negative 1.7965. And again, if I were to store that as the variable and do 6 to the x, I would get this as a decimal. Turning it into a fraction wouldn't help me because it was rounded, but to compare it, I could do 1/25 on my calculator and see that I get very close to 0.03999 is very close to 0.04. So no worries there, and I do like this answer. Okay, so let me move these down a little bit because I'm going to do these examples in a bit, but I want to do this last example. This example, you could find something like this potentially in a compound interest problem. Now, this is not a compound interest problem per se, but the maneuvering that you would have to do here is something that you could potentially find in a compound interest problem. Well, this you could look at it and say, well, this is much different than what I've been used to dealing with, but it's really not. And I'll try and draw on it for a second so that you kind of have the sense of what I'm talking about. These guys were, in fact, I'll look at number 2. This was a base to an exponent, and I'll circle it because that's where the variable is, which gets you this thing called a to get here. Well, that's exactly what's going on here. We've got a base, as funky as it is, it's still a base, to an exponent, which is where the variable is. So I circled it to draw attention to that. Gets some type of answer. Well, from here, I just need to, again, address this from the writing it in this exponential form, taking it into log form. So I'm going to write log, and the base is this ugly thing here, but I'll just write it as is, 1 plus 0.025 to the 4 over 4 to get 2 equals 4x. Okay? So from there, I can write the change of base formula, which is going to give me log to get 2 over log to get 1 plus 0.025 over 4 equals 4x. And then because I understand that this is a really funky number, I'm just going to leave it like that for a second. This is kind of an example of writing this with a little sense of anticipation of the type of answer I'm going to get. So the only thing I'm going to do here is multiply both sides by 1/4 to get the x by itself. Okay? And that'll get x alone. You might be sitting there saying, well, why didn't you divide by 4? Well, do you want to write divide by 4 over here and figure out that mess, or would you like to do something a little more elegant and multiply by the reciprocal? So this is going to give me x is equal to 1/4 times log 2 over log to get 1 plus 0.025 over 4. From there, I go on my calculator, okay, and just do 1/4 times log 2 divided by log 1 plus 0.025 divided by 4, closing that set of parentheses off, and closing it off again for the distribution of the 1/4, and it gets me 27.8124. 27.8124, which is, again, an estimate. Okay? So that is how we apply the idea of log. You can check that on your calculator. I feel decently confident. But I'm going to save that time and go down here a little bit. Okay, so log is the duct tape method. Why do I call it that? Well, again, if there were one method you had to be able to rely on log, because it does all of our problems. And I want to talk about these problems, 3 and 4. They were in the other videos, okay? But I want to talk about them from the standpoint of using all these methods, okay? So I hope I don't get too wordy here, but I'm going to talk about these, looking at this from kind of all three methods here. I don't know if I'll do both examples. We'll see how, from the standpoint of time here. Okay, so the one thing here, if you notice in number 3, is it should just jump out at you that x equals 3. And that's the feel method. Because you sit there and know, well, if I cube 5, I'm getting 125. Now, let's take a look from the change of base standpoint. Okay? Change of base would allow us to look at that and say, well, you know what? 5 is already a base of 5, but I could rewrite that 125 as a base of 5. So I could write 5 to the x equals 5 to the third. Well, from there, I hope you realize from the 1 to the 1 principle, you're just getting what you said you were going to get before, which is x equals 3. Okay? So now, using the log method, there's not a lot to do here. You could just sit in there and say, well, I'm going to write that in log form. So you would write log base 5 to get 125 equals x. And then the change of base formula, which you should be pretty good at by now, which is log 125 over log of 5. And again, the base is 10, which is not written, it's understood. And that allows me to go to my calculator and just get log 125 divided by log 5, and I in fact get 3. Nothing to round. Nothing to round should indicate that you probably could have done this with the field method or the change of base method. But if you see, they're all the same. So I'm going to take a moment here and do this on another page. Let's cut this for a second. Go forward. Okay? And I'm going to do this by feel, if I can, change of base, okay, and then log. Okay, well, if I look at this from a feel standpoint, I'll be perfectly honest with you. I don't know how to make an exponent that's going to get me from 16 to 32. So, you know, I don't necessarily have a feel for that, so I'm just going to kind of forgo that for now. And again, the change of base, well, if I sit there and say, well, how can I make these the same base? 16 and 32 are in the same family. So I just write 2 to the 4th to the x equals 1 over 2 to the 5th. And again, this problem is in the other video. And I could use the negative exponent principle along with the power principle here. And then the 1-to-1 principle says that 4x has to be equal to negative 5. So I get negative 5 quarters, which is also negative 1 and a quarter. And then for the log principle, it's as simple as, excuse me, I'm sorry. Again, moving to the log notion, all I need to do is rewrite this exponential form as a log, which that's log with a base of 16 to get 1/32 is the exponent. Again, don't lose sight of that mantra, that a log is an exponent. A log is an exponent. So it makes sense that it says equals x. Log equals x, because x is the exponent. Okay? So just to make this quick, we're going to get log to get 1/32 over log to get 16 equals x. And then when I go to my calculator for that, I'm going to get log 1 divided by 32 divided by log 16, and hopefully I am in fact getting the same answer I got before of negative 1 and a quarter. Okay, so what does this demonstrate? It demonstrates that for problems that you can do by feel, you should be trying to do them by feel. The answer should jump out at you. Some feel problems can be written with a change of base, and if they can, then you could even do that with a log. But log is great because if you notice, it does problems where you really can't feel the answer with any exactitude, and you really can't change the base. So that's why I call it the duct tape, because it can do every type of problem. So again, just to wrap up, these are 3 approaches that I hope these 3 videos tried to bring the light better. It takes a little practice. To develop feel takes practice. To do things mechanically takes practice. And to do things that are a little bit new to you, like log, they take practice as well. So enjoy. I hope this was useful.